So this is the first of 5 videos that will review the process of naming and writing formulae for a variety of compounds. This is known as nomenclature, so let's get started. Just to remind you, what does nomenclature mean? Well, what it means is essentially an act or process of naming. And so we take a chemical formula and we have to be able to come up with a name using a series of guidelines. And it's also then a system of symbols. And from those symbols, from a name, we get those symbols. So we put together the chemical formula. And that comes up in a particular science. It comes up in a few sciences, but for us, the important one obviously is chemistry. So I really can't overstate the importance of being good at nomenclature and naming. Okay, it's a must-have skill if you want to proceed in the rest of chemistry, which is really taking for granted that you can write a chemical formula from a name or vice versa. So it's really important. It does require some practice, but luckily I have an opportunity to practice. All right, so let's carry on. So first things first, just to remind you how we come up with the charge on an ion. For organic or ionic compounds, we want to quickly come up with the charge of both ions involved, and that allows us to put things together. So of importance here, and I've just isolated the main group elements, that is the groups on the extreme left-hand side of the periodic table and the extreme right-hand side, and we want to focus in on these Roman numerals. So these Roman numerals, 1A, 2A, and we go across on this side, 3A, 4A, 5A, 6A, 7A, and 8A. So those are important, those Roman numerals, because the Roman numerals tell us the number of valence electrons. So that's our first step, is very quickly get valence electrons. And once we've done that, we have to decide what is going to happen to those valence electrons. And again, you may recall on the left-hand side of the periodic table are the metals. Metals have a low electronegativity, and so metals lose electrons. And so if they lose electrons, they form positive ions, which we sometimes call cations. Okay, so metals always form positive ions. They always lose their valence electrons. On the other side of the periodic table, we have the nonmetals on the extreme right, and so the nonmetals have a high electronegativity, so they will gain electrons, and when they gain electrons, they form negative ions. We sometimes refer to these as anions, and so they will always be negative. A metal ion will be a negatively charged ion. Now, so that's the first thing, Roman numerals. Second thing, metals, they're going to lose, nonmetals are going to gain. So then the next thing is, what's going to be the common charge? Well, it all depends on how many electrons they're going to lose to become stable, or how many electrons they're going to gain to become stable. So on the left-hand side with the metals, it's pretty straightforward. A metal will simply assume the charge of the number of valence electrons, and it's going to be positive. So something like sodium, it has a single valence electron, it's a metal, it's going to lose that electron, so it's going to form an Na plus cation. Positive ion loses its lone valence electron. Versus something like, let's say, we'll have an oxygen. So oxygen over here is in group 6, so it has 6 valence electrons, so it's going to have to gain electrons because it's metal, so it's going to gain 2 to get 8, so it becomes a negatively charged O2 minus ion. So these ions on the right hand side will form negative ions based on their charge and how many electrons they need to gain. These ions on the left hand side will form positive ions, and they will lose the number of valence electrons they have. All right? So, ionic compounds, binary ionic compounds. So, a metal combined with a non-metal. Binary simply meaning we're only talking about 2 different atoms here, or 2 different ions. Pretty straightforward in terms of the process. A name is generated by listing the metal first, then the non-metal, and we change the ending of the non-metal to "-ide." And the other thing is the formula for the neutral ionic compound is arrived at by putting together the ions to obey the zero-sum rule. And what is the zero-sum rule? Well, here's a quick example. So this is a big hunk of sodium chloride salt. And so that smaller ion is the Na ion, and it happens to be Na+. This larger green ion is the chloride ion, and that's a Cl-. So when we put these two ions together to generate a formula, we have Na+ and we have Cl-, and we want to put them together. Well, there it is. But the sum of these two ions has to add up to 0 because the overall charge of this compound is 0. And so we look at the ions. 1 plus 1 minus, well, that equals 0. So NaCl, the formula, does obey the zero-sum rule. Okay, so that's what you're looking for in terms of obeying the zero-sum rule. Just a quick note here: if you recall ionic species, the formula is actually called a formula unit because this big block of NaCl does not incorporate how many different ions there are in the big block. We look at the simplest whole number ratio of species of ions. And so there it is, 1 sodium and 1 chlorine. That's the simplest whole number ratio. That's called the formula. Okay, so we're going to put together some compounds now and write the formula and the name. So compound consisting of magnesium and oxygen. Well, let's quickly go back to our periodic table. So here's magnesium, group 2. 2 valence electrons. It's going to lose both of them because it's a metal, so that becomes an Mg2+ ion. Oxygen we already looked at. It's going to form an O2- anion. So we have Mg2+ and we have O2-. We want to put those together to obey the zero-sum rule. 2+ and 2- equals 0, so we only need one of each. So there's the formula and the name, metal, followed by the non-metal ending in "ide." So magnesium oxide. So there's the formula. Well, how about magnesium and phosphorus? Well, we already know what magnesium is, still 2+. Well, phosphorus over here, it has 5 valence electrons, 5a, so it's going to lose or gain 1, 2, 3. It's going to gain 3 to become a stable ion. So we have magnesium 2+ plus P3-, and so Mgp, but that doesn't obey the zero-sum rule. 2+ and 3- does not add up to 0. So we're actually going to have to come up with different numbers of these, and we in fact, as I'm sure you realize, will require 3 magnesiums and we require 2 phosphide ions. So that now obeys the zero-sum rule. 2+ times 3 plus 3- times 2, and that equals 0. So that's a neutral magnesium phosphide ionic compound. So that's what we mean by the zero-sum rule. Now you may have seen this in earlier incarnations of a chemistry course or early science courses, sometimes referred to this crisscross rule, where you take the magnitude of the charge of an ion and make it the amount or number of the other ions. So that's where we get those subscripts. So there's the subscript 3 coming from the charge of the phosphide. Okay? But really, think about it in terms of the zero-sum rule. That's really what you're trying to do. Now, one other thing we have to be able to deal with is certain transition metals that have more than one charge. And this is not uncommon. You'll see this in the D block elements especially. And we have to come up with a way to address this, because what you can end up having is compounds made up of the same 2 elements that are quite different. And I have an example of that here. So we have these 2 different chemical compounds. They're both in solid form, and they're both made up of iron and oxygen. And they are quite different though. And so we have to be able to deal with that in terms of the name. So this is actually iron 2 oxide, 1 atom of iron and 1 ion of iron and 1 ion of oxygen, and iron 3 oxide, 2 irons and 3 oxides. And so the stock system, that's what this is called, is it allows us to deal with that. Other than that, everything else is dealt with in the exact same way. just to give you the heads up, then you have a periodic table that looks something like this. At least it's posted, so you can refer to that. And most periodic tables will, in the transition block, indicate the common charges. So there's iron again, a 3+ ion and a 2+ ion. And so it is really how you approach this is you have to sometimes consult the periodic table when you're not sure. So let's look at just starting to how we would sort of put this together. So you look at your periodic table, you're looking at the most common ion charges, also known as the oxidation states, and for iron. Now if you're not sure, you need to look, and so we go back and look, and so there's iron, sure enough, 2 different charges. So what are the possible ions? Well, you have Fe3+, and we have Fe2+. So the first thing, you can't be afraid to go look at the periodic table if you're not sure. Now, in terms of naming this, and this then comes through in coming up with the name of a compound containing these ions, we use Roman numerals. So the cations, 2 different cations, the charge is given in Roman numerals following the name of the metal. And so for iron 2+, we're going to give this name iron 2. So there's, in naming purposes, this is actually the name of the ion, the iron 2 ion, and the iron 3 ion, and we'll see in a minute, we just take that iron 2 and that iron 3 and it becomes part of the name in a compound. So that's the next thing to realize. These actually are acceptable names for ions. The Roman numerals preceding or following the name of the actual metal. Okay, so once you understand all that, it's pretty easy to put things together. So again, if you go back to iron, well, we know we have an iron 2 ion and we know we have an iron 3 ion. That's 3+ and 2+. We're going to put this together with chlorine. Well, chlorine is a group 7 nonmetal, so it has a charge of 1-. It has 7 valence electrons, needs 1. So we put that together, we get FeCl2, and that's going to be called iron 2 because of the 2+ chloride. Fe3+ and Cl-, well, formula's pretty close, not the same though, and that then needs a unique name, and it has a unique name because the name becomes iron 3 chloride. So that's how you deal with multiple charges for the same metal. They're found in the transition block. Let's do another one, copper and oxygen. So if you go look at copper, the periodic table, there's copper Cu +2 and +1, 2 different charges. And so copper 2+ and copper 1+, the copper 2 and the copper 1 ions. And they're combining with oxygen, which we determined already was O2-. So we have CuO, obeys the zero sum rule, and that's going to be called copper 2 oxide. And this one is going to be Cu2O. 2 positive charged ions would balance 1 2- oxygen or oxide ion. So that becomes copper 1 oxide. So again, a unique name for a compound with a unique formula. That's what the stock system allows us to do when we have multiple ions. Finally, let's look at zinc. Okay, so zinc is in the transition block, so we want to have a look. And so there's zinc, but it only has a single charge, +2. So zinc does not require the stock system. So it's just Zn2+ with oxygen 2-. So that becomes ZnO, and it's just going to be called zinc oxide because it doesn't have multiple charges. So, as I said before, chemical nomenclature, it's important, it requires practice, but I've provided you with lots of practice. And that concludes this video.